Hello everybody and welcome back to another video. So in this video we're going to be discussing the Josephus problem approach 2. So let's begin. Okay guys, so we discussed how to solve this problem in the previous video. If you didn't watch that video, so please go ahead and watch that. So because I'm not going to be explaining how the Josephus problem, really works. So first of all, the main concept for approach 2 is that if we find out n minus 1 k, then we can also figure out n comma k. So let's say that in this scenario n is 5 and k is 3. So we could make it like this. We have 5 people standing in a circle. 1, 2, 3, 4, and 5. Um, and now let's actually go ahead and solve problem. 1, 2, 3 eliminated. 1, 2, 3 eliminated. 1, 2, 3 eliminated. 1, 2, 3, and this person is eliminated as well. So our survivor is 4. So now let's try to solve it for n minus 1 and k. So n is 5 and n minus 1 would be 4 because 5 minus 1 is 4. So let's go ahead and do this over here. So we have 4 people standing in a circle. 1, 2, 3, and 4. So 1, 2, 3, eliminate. And k is going to remain the same. So k is going to be 3. So 1, 2, 3, eliminated. 1, 2, 3, eliminated. 1, 2, 3, and this person is eliminated. And our survivor is 1. Okay, so we figured out that for n and k, the survivor is 4. And for n minus 1k, the survivor is 1. So over here, let's say I'm actually going to write down this problem again. So we have 4 as a survivor. For I'm just gonna write down it just this, but in the order like this: 4, 5, 1, 2, 4, 5. Oh, I'm missing 3 over here. Okay, so now let's give each of these positions. So 1, 2, 3, 4, and 5. So these are the positions over here. Okay, so now what we're gonna do is uh as we know that for n minus 1 the survivor is 1, right? And now if we check the position of 4 and which is 1, so this means that 4 is the safe position slash survivor. So now how do we prove this? To prove this, we add it by k. So I'm going to show you that just in a sec. First of all, I'm going to write down the positions over here, which so 1, 2, 3, 4, and 5. And now I'm actually going to write down the main problem. So 4, 5, 1, 2, 3. And okay. So now what we have to do is we have to add the position, by k. So in this scenario, k is 3, right? So I'm going to do this. So 1 plus 3 is equal to 4. So as you know, 4 is the element over here. So this brings us there. So this means that this is the correct position. So that is how we find the position. So same with 5. 2 plus 3 is 5. And this gives us 5 over here as well. And over here, so it is 3 plus 3. This gives us 6, right? But remember that we're doing this in a circular manner, and we have to use the modulo operator over here. So we do it by n. So 6 modulo 5, or the remainder will be 1. So as you know, then the remainder over here will be 1 as well. So yeah, this is how it works, and this keeps going on, etc. and etc. So this is how the approach 2 works. It is a much easier way, and I will explain the complexity analysis at the end of the video. But for now, let's actually go ahead and start coding this out. I'm going to first of all start off by creating a new file. Just as approach to pi, or you could call it anything you want. Okay, so now what I'm going to do is I'm going to define a function over here. You can call it anything you want. Find the winner. And over here, we're going to be needing a helper function as well. So n comma k. And this is going to be our helper function. I'm just going to call it Josephus. And it's going to have n. So now we first have to do our base case. So the base case is if there's only one element left, we're going to return that element. So the index of that element is going to be 0. So we're just going to do it. So now over here, we're going to do our main recursive case. So what we're going to do is we're going to return Josephus with n minus 1 plus k modulo n. Okay, and now over here at the main function, we're gonna do return Josephus n plus 1. So what this does is that we're gonna return the last element remaining, but it's gonna be at a 0 index, right? So to make it at this more readable way, we just add a plus 1 to just give the right index, like starting from 1, because we won't go like 0 1 2 3 4. We would go 1 2 3. So yeah, that's why. So now let's actually go ahead and then test our function out. So print, find the winner, and I'm just gonna do 5 and 4. So run this. Okay, we're getting a problem over here. So let me go ahead and check this. Oh, we're getting a recursion error. Oh, okay guys, so I actually spotted two problems over here. So one was that we were missing k in the parameter, and when we were calling this, we were missing the step, and to adjust the indexings, we need to have k over here and over here. So these were the only two problems, and I tried testing with 6 and 2 as n and k, and as you can see, it threw back the answer 5. So I think, yeah, this is how pretty much how you code it out. And now let's go ahead and check out the complexity analysis for this. Complexity is pretty simple. So first of all, our base case over here, this gives us a time complexity of O of 1. And over here we have our main recursive case where we're gonna keep subtracting n minus 1, and we're gonna keep on doing this until there's only one element left, right? So this gives us O of n. So thus the time complexity is O of n. So this is actually a better approach, but the third approach we're gonna discuss in the next video, the last approach, approach 3, it's gonna be really good, and it's the best approach. So, and I think this is pretty much it for this video. Thank you guys very much for watching. Like the video if it was good, and subscribe to my YouTube channel, and I'll see you guys in another YouTube video.